Hello, hello. Aha. Hello. Oh, it's like a whole hello.
Good
Hell.
afternoon.
Oh, she went. I mean, not that it's a competition, but good afternoon. And good afternoon. Wait, who? Okay,
Hello.
hello. Okay, that was definitely Michaela. The first good afternoon was Sarah. No, who was Samantha? Who was the first? Not the first. It's not a competition, but it totally is.
I said
Who?
hi.
Oh, that was Allison. Okay. Hello, hello, and hello, Michaela. And wait, and there's all these. Wait, okay. And oh, and definitely, even whether you're saying hello or not, hello, Samantha Davis, because I totally said that's awesome. Okay, wait. Hello, Dennis. You were totally again, not that it's a competition, but if it's gonna be any. So hello, Dennis. Good afternoon, Bree. Good afternoon, Juliana. Hi, and there she goes, Samantha. Oh, like I said, I wasn't gonna call attention to. Okay. Good afternoon, but that's fair. It's totally fair. Good afternoon, Juliana. Hi, Penina. Hello, Sarah and her iPhone. Good afternoon, Mario. Hello. Wait, hello, Samantha Davis. Wait, question mark? Did I? Oh, question mark. Okay, hello, Samantha Davis. Good afternoon, Key. Oh, exclamation. Oh, okay. Sorry. See, this is why I should not respond so quickly to these things, because then I end up calling attention to exactly the right. It was a typo. Sorry. Right. I should read. This is like that thing. Good afternoon, Samira. Hi, eyes iPhone. Okay, yeah, I'm not going to comment on that, but I totally am, because what does that mean? And good afternoon, Christopher, and good afternoon, Tawiba. And I do know, Tawiba, I know you were here like minutes early. I'm very aware. I know I'm just saying hello to you now, but I know you were here before. Good afternoon, Alexis, and no problem. Oh, Alana, got it. Cool. Thank you. Totally appreciate that clarification. And wait, there's a direct chat. Oh, and the closed captioning is totally cool. I'm never clear on that closed. I'm totally psyched for the closed captioning. I don't know. I guess it only helps the person that requested it. It doesn't help anybody. I'm all for any of the. Oh, I guess you can show the captions on your. Oh, I see. Okay, sorry. This is not a joke. I'm still trying to figure out how that whole thing works. And you could turn them on YouTube, I believe, right? At your own. Correct me if I'm wrong, or in the private chat, but I believe when you play these YouTube things, if you want, you can have them subtitled. If I believe that's right, which I know is helpful to some. All right, wait. Sorry, I'm reading direct chat, and we will start obviously. Okay. Hold on. Sorry. Hello and good afternoon, Dante. Thank you for saying that. Hold on. I'm just responding to a direct chat. Okay. So I think that's hello, everybody. And we will get rolling each day. Hopefully we roll a little bit. Oh, and there's Dennis. Yes, Dennis. Thank you. I totally see that. That's 1,000,000 points. Thank you. Is that John J? I'm not gonna see, always do that. People have the guts to show video, and then I ask all these personal questions and make it harder. But is that John J Library? No. Okay. All right, I'll stop asking. And thank you, direct chat person. Okay. So we'll get rolling in a second. Quick things. When I was sending back, so again, we're up to homework 2 now, but it's still not too late to hand in revisions or uploads of homework 1. Hopefully you noticed hopefully everybody got something back for homework 1 if they did it. Some people got extensive feedback. Some people just got points. That's a little bit random. That's a little bit scattershot. If you just got points, but you didn't get extensive feedback, it might just have to do with exactly when you turned it in or something. That's not necessarily personal. If you got points, but you didn't get feedback, if you didn't get all the points yet, hopefully I'm thinking that it's just self-evident to you what you could still turn in to get the rest of the points, and then I'll probably give you more feedback. But if it's not evident or something, let me know, and I can you could just say, can you please re-look at my assignment and give me more feedback or something? Like, I'll do that. Just sometimes I'm scattershot about it. But anyway, same thing with homework 2. Many people turned in homework 2 right before class, which is when it was due. That's great, but I haven't looked at it yet. But I totally see. In fact, I may even comment in a minute. I definitely appreciate those of you who have turned it in, and we are going to start talking. I have many more extensive things to say about what's implied by the last question on homework 1. There's there's more to unpack about the last question on homework 1. But as many of you noticed, homework 2 sort of starts with some of those issues. So in a moment or two, after I make a couple more announcements, in a moment or two, I'm probably going to get right to homework 2 and start talking about the first couple exercises, and then I'm going to pause and relate them back to a more extensive discussion of the last question on homework 1, homework 1B. Again, all of this is to say, if you still want to hand in things about homework 1, that is totally fine. Okay, hang on. What oh, someone's here. Okay. There was one other thing, but when I was going back, hopefully, as far as I could tell, any game turn that you've handed in or any participation game like portal thing that you've handed in, hopefully, those are quicker and so forth, but they're worth a lot of points, as you're seeing. Hopefully you're all seeing that you've all gotten all those back. Like, that's just a ongoing dialogue between you and me, and those portals that are not game turns, the portals that are not daily turns, I see that a lot of you are understanding correctly that you can use them at any time, and then you can re-upload new things later when you use them again. That's all exactly right. So some of you have already gotten multiple points, or like double points or whatever, for 2 different days that you submitted video, or 2 different days that you submit, that you used showed video, or whatever, and that's all great. Just again, a reminder that with any of those portals, when you do a submission for a day, like if you're one day saying, here's a bunch of notes that I took, here they are, if that's the notes that you're submitting for the day, even if they're multiple screenshots or whatever, please compile them all into one file. Just submit one file for each submission, please. There's a lot of reasons that are sort of evident, and there's some reasons from behind the scenes of how things look on my end when I'm grading. It's very difficult, honestly, to deal with multiple JPEGs or what, or PNGs or something that are meant to be one submission. And honestly, again, one of the reasons I'm strict about these things, about weird things like formatting, is it really matters once it comes to exam time. You do not want to give me more than one upload for an exam, which we have to talk about in a minute. So please note that, or send me any questions if you have any questions about how that works. 2 more quick things. Those game turns, again, the daily game turns, if you say anything at all in a daily game turn, even just like I said hello, then you get, you get the 5 points. It's obviously, the more you say and the more that you contributed, I think the happier we both are. But it's meant as a moment of reflection on how you did participate or contribute. So if you just said hello, fine, and you say, I just said hello, and you upload it and you get 5 points. But that's the only, ironically, the only thing besides exams that I really am strict about the timing is those daily game turns, because they are meant to be daily reflections. So with a daily game turn, if you submit it the next day, you get 4 points instead of 5. So if any of you ever got a 4, that's why. But anything after the next day, just forget it. It's not worth it. Okay, and that's also just to practice. I don't want you to get too hung up about deadlines with the homework. I want you to just, I want you to feel that late is better than never with the homework. But with exams, we have to be strict. So I hold the line with the daily game turns just so that you understand that in some contexts, deadlines do matter, and certainly exams are one of them. I think the lights are, things are lighting up in the chat. Oh, and there's people in the waiting room. Sorry, that's probably what you're telling me in the chat. I'm sorry, hold on. People in the waiting room. And I will, but I see there's things in the chat in a moment. I'm going to look in the chat in a moment. Let me just remember if there's any other, I will look in the chat in a moment. I just want to get these announcements off my chest before I forget. One other thing I like about, part of the whole purpose of these participation game portals, and particularly the daily turns, part of it is it's feedback in both directions, you and me. It's keeping you and me like together in the same yellow submarine. And so when I go through those daily turns, even though I'm as quick about them as you are about them, it kind of like reminds me or updates me of what's going on in the class from your perspective. And so, for example, and here's someone else in the waiting room. For example, I did notice going through them. Honestly, I noticed with one person was submitting a bunch of things, but I could tell from that person's screenshots that there were things in the chat from other people that I had missed. And those people are polite or whatever. So they never, demanded anything of me about them. But I'm seeing things in the chat that I try to be vigilant about the chat. But I mean, I know there's things in the chat right now, but literally in those daily turn screenshots from person X, I saw things in the chat from person Y that I kind of feel bad about having missed now. And if I get a moment, I'm going to directly chat that person Y and acknowledge. But so this is just to say, it's like you're all helping each other. The more you can sort of give me glimpses of how you're experiencing class, it really does help me help you. Actually, I'll be blunt. There is at least one person who submitted an answer to question 4 in the homework, said something like, I think the thing, someone submitted the answer 1,000,000, kind of as a joke, but kind of to see if then I would comment that the answer 1,000,000 was wrong. And then if I could give them points for a wrong answer. Listen, even if that was a joke, first of all, I think it's funny. I do. Second of all, it shows that someone was paying attention to like a lot of different things. But third of all, actually, honestly, again, like challenge accepted. If someone wants to submit 1,000,000 and you know who you are, I know who the person was who did that. Like, and I might remind that person if he or she forgot. But someone who wrote 1,000,000 as an answer, like, I'll say that's wrong and I'll give you points for a wrong answer. Let's see how far we can, I'd like to see how far we can take this wrong answer thing. For real. And if someone else later on in the chat says, oh, that person who said that was blah, 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 she or he deserves points, I'll consider that multiplayer co-op. I mean, whatever we can do to actually make this a group activity and a live, real engagement, I think is for the best for all of us. So, someone else is in the waiting room. Okay. I'm going to but I think that's enough. And I know I have to address the exam issues. I will. I think you saw on the Google, like, we're not forgetting. Yes, there will be an exam. Yes, it's going to be due Sunday night at midnight. As I think you saw, we'll address that. But all right, I'm going to pause for a second because I know the chat light is blinking green. Hold on. All right. So. Okay. Chat. Oh yeah. Oh my God. Zoom updates are so annoying. I know the update right in the past. But thank you, Evelyn, for saying so. Too bad. So I'm going to take a risk here. And oh no, okay, Evelyn wrote that 7 minutes ago. So maybe Evelyn heard the little part that I was just saying about the answer 1,000,000. It might or might not have anything to have done with her. I don't know. I'm just saying. Okay, Dennis, cam scanner is good. Oh, cool. Cam scanner, good tip for everybody. That counts as multiplayer co-op. You could definitely screenshot that. Yes, cam scanner is a good way. And you can help each other there. And yeah, there are other ways as well. But yes, thank you. And again, that shows that you are following like what I'm saying. So thank you. Oh, love that app. Great. Thank you, Bradley. These things count as something. Good. So cam scanner. Okay. No. Wait, Dante. Well, anybody. Wait, no. I think, Dante, you're doing the right thing. Honestly, Dante, I'm going to say this. I don't know if this counts as wrong answer. First of all, I remember some of the people that were not doing what Dante, I don't think you've done it wrong. I am saying I want them all. I do want everything compiled into one document. That is what I want. And that's, again, that's particularly important for an exam. Like if there's, I'm going to scroll down. I should stop responding until I read everything. But no, I am saying the only thing that wants multiple uploads, I'm saying, like, if you upload one thing on one night for either a regular homework or a participation portal, either way, if you submit something on one night and then a couple nights later, you want to upload something new or a revision of the old document, like a more improved version or something, then what I'm saying is don't take down the old, just add to your old thing, which people are doing. I mean, it does seem to be working if you do it right, like just add another attachment or whatever that option is. I'm saying don't take down old things, but so the only time I should see multiple files in one portal is when it basically encompasses multiple nights. And then that's good. And that's like good. But I'm saying in any given thing that you give me, it should be a file. It should not be a group of screenshots. And I do want to make sure that's clear. I mean, I think that, so I'm going to check back with Dante in a second, just to make sure. And Dante, if you write something in the chat, maybe you already did, that says like, oh, got it, or whatever, that totally counts as closing a conversational path. And you could submit for those points. Because I do want to make, honestly, everybody, 1 year, I got in not even in an online class, in an in-person class, 1 year, not too long ago, one student, both his midterm exam, and it wasn't him, I mean, both his midterm exam and his final exam, like when he submitted it, it was like 23 JPEGs and they weren't even numbered. And there was no way I could go, it was like a nightmare to go through, let alone to correlate the points and give him a fair score. He literally made it impossible for me to adequately give him a grade that he deserved without like toppling the whole rest of the class and never getting to any. It was really problematic, and it was disturbing because I felt like we had a number of opportunities to practice this with all the homework. So like don't, and it ended up really hurting him on it, because even though I tried to just do what I could for him, I could not navigate his exam. So that's what this is all about in the end, is that your exam is one PDF or one Google Doc. Okay. So now, okay. Evelyn heard it all. Okay, good. So I'm going back to the chat. Okay, and I see in the direct chat that someone's reaching out for Evelyn. So cool. So that person, it's in direct chat. So I'm not going to say that person's name, but they should still screenshot it and they will get points for multiplayer co-op, so to speak. Okay. Oh, okay. Oh, okay, Dante. No, I'm glad. All right, thank you, Dante. And again, Dante, you can submit this conversation we're having right now, you and me, is very helpful to a lot of people in the room, I think, not just you, Dante. So there's more than one way you could submit this whole conversation for points, honestly, because now I get what you're saying. Okay. Yeah. So, okay, right. You are understanding me. I'm being confused, but in terms of what Dante has put at the end of the public chat, where he wrote, no, I mean, for the ones due at the end of the session, I was just putting them all on one thing with dates and times instead of just submitting them every day. Okay, so I do get what he's saying. And yes, he's saying a different thing. Like, he's not crazy and he's following the whole, but on what he's saying, right. Okay, let me tell everybody, right, that's not the preferred way. I would rather you, and even now, even that's what he's been doing for a couple of days, it would still be better to upload those things from the last couple of days when he gets a chance, like not, Evelyn, that's funny. Like, to all of you, better to be submitting as you go on a daily basis. Strangely right now, because this is one class, because it's the middle of summer, somehow I think I'm on top of getting these back to you guys right now, but it's just on the edge. Like, if you keep just submitting as you go, then you can get the points as you go, and then we won't be in a whole big panic at the end of the semester. We don't want you or me to be under a huge big pile at the end of the semester and rush to get through it all. Neither you nor me. So no, please do. Plus, you want to have as little mystery as you can at the end of the semester of what sort of your grade is vaguely looking like before you go into the final, right? So yes, maybe that wasn't clear. Please upload these things as you go, and you can just keep adding those uploads as you go. Okay, and if that is clear to Dante and or anybody else, if you could make it clear that it's clear in the chat, that would be great. Okay. Okay, quickly, and I gotta get, great. Oh, thank you, Allison. See, that's so, okay, great. Okay, thank you. I mean, I don't know. And again, that counts what she just did. And it, oh, and that, okay, and I just saw one in the direct chat. That counts as the portal closing a conversational path. This is, like, it's helpful to all of us. This is all, it's all, you could thank Amazon for inventing the whole idea of first they give you a product, then you give them customer feedback, and then they give you feedback on your feedback, and it goes on and on and on. But somehow that's helpful to everybody, and that's why Amazon is in charge. Okay. There's someone else in the waiting room. No. Okay. So, wait a minute. Nodes and antinodes. Now, wait, that's a very good question. Penina, that is a very good question. We definitely have to get to that. Has that already come up in lab? Oh, did you do, wait a minute. Oh, because you did lab. Yes. Okay. Okay. All right. Okay, thank you. And Samantha and Allison, that's very helpful to your colleague. That totally counts as multiplayer co-op. Okay, Penina, that's a good question. I'm gonna try to briefly answer that right now because you're asking, but it's gonna be okay, because I came from lab today. I'm gonna briefly answer it, but then as you all know, you sort of do things in lab first and then we get to them in lecture recitation. So sometimes there's a little bit of a delay or like what do you call that? Sometimes there's a latency, but okay. So yes, we're going to do a brief answer, and then but since we're not quite up to the wave thing yet in lecture, it'll be a brief answer. But I'm looking at Evelyn's answer. Do I agree? Wow. Yes, I do agree. I don't know if that's helpful or not. I mean, it is helpful. I mean, I do. First of all, I agree with what Evelyn said. So thank you. Yes, I do agree with what Evelyn's saying. Can I add or wait. Oh, okay. Thank you, direct chat person. Got it. Good afternoon to you. Cool. Okay. The nodes. Yes. I mean, Evelyn's answer is even though we're not quite up to waves yet here, and we will be shortly, when wave pulses are going back and forth across a medium so rhythmically, so regularly that they start interfering with each other and falling into a pattern of reinforcement and cancellation. When wave pulses, crests and troughs, are going back and forth over and over again on a medium so that they start canceling each other out, that's called destructive interference, and reinforcing each other, that's called constructive interference. After a while, wave pulses can fall into a pattern where instead of, for example, looking like this or looking like crests and troughs going like this, they'll start just looking like this. And there will be points in the medium, there will be locations where all motion seems to cancel out always. There will be points where we never observe any motion at all, any crests or any troughs, because crests and troughs are perpetually canceling each other out. Those points, those equally spaced points of no motion, are called nodes. All of this is what Evelyn just said. If what Evelyn said is clear to you, that's good enough. Great. I'm just expanding slightly for whatever reason. And the points where maximum displacement from equilibrium seems to continually reoccur, where maximum reinforcement, where the most constructive interference seems to be going on perpetually, points that keep flipping from huge crests to huge troughs, those places are called antinodes. Again, that is consistent with what Evelyn said. It's a slight expansion. It's a great question. We, of course, are going to get to all that, but okay. I'm now looking. By the way, okay. Well, hold on. Wow. Yes, and see, there's somebody even in the chat. You guys are giving feedback to each other's. I got to open a portal for that. I didn't even know it was possible. You're literally giving likes to one of your own. God, if you could do that easily, freaking start liking my videos, for heaven's sakes. What is that? No, I'm just kidding. Wait, and the numbers are going up and down. That's amazing. I didn't even know you could do that. Okay. See, this is a feedback generation. I don't need to explain this all to you. You all understand about feedback. Okay, so no, that is great. So first of all, right, the Evelyn's picture is great. I'm just going to say, and it would be great too if since Penina asked the question and it's legitimate, but it's like slightly to the side. It would be great if at some point, Penina, if you could just say that the answers are good enough for the moment, that they may not answer your whole life, But if they are basically clarifying for the moment, it'd be great. Or not, if you could tell us, that would be great so we can move on. But I'll also say to everybody, not only is Evelyn's explanation good and her picture good, I will say there's a portal for that. Great. Okay, it works. Well, that's fair. It works. We know what that really means. But okay, cool. Thank you, Vanina. But also just side note, there is a portal that's called Worth 1,000 Words. I mean, a participation portal. And I guess that's a bad title. Some of the titles are way too cutesy for sure. But Worth 1,000 Words is supposed to be because like a picture is worth 1,000 words, like that old expression, yeah, right? So that portal, I think actually a couple people got it confused. I think they thought it meant like if you submit 1,000 words to the chat, you get points. No, it's saying if you submit a picture of some kind, like maybe a screenshot of your own like solution or something, or like what Evelyn just did. That's really helpful to everybody. It breaks up our day. It helps us out. So that's an example, what Evelyn did of something she can submit to the portal known as Worth 1,000 Words. And again, she can like triple dip it. She can also submit it as an answer, blah, 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 blah. Okay. I like the cute. You like the cutesy. Okay, cool. Thank you. I appreciate it. Okay, I probably shouldn't even use the word cutesy because it's so cutesy, but thank you. All of this for anybody who's speaking of cutesy. I mean, even though, well, no, I'm not going to say. All right, I'm going to let's get back to. Okay, we got to get to business here. But yeah, the whole participation. If it's not clear already, the whole participation portal idea that you submit your own evidence of your own, that you have to show, that you have to like apply for your own points. All of that, for what it's worth, is 100%, and all the cutesy names. It's all based on Nook Miles and Animal Crossing, if that helps anybody. And if you don't know what I'm talking about, don't worry about it. It's probably just alienated 70% of the room, but it's totally just a Tom Nook thing. Okay, look it up. Okay, so we're gonna go to fit. Oh, thank you. Okay, I was hoping for that. See, I needed that feedback, so I don't. Okay, okay, we have to go to physics. One last thing though, because I know it's important, or I know people care, is hopefully it's clear. Like I took all your, nobody wrote me and said like, no, don't let us work on Sunday. Like I can't. So I took your feedback seriously. And so the exam that will be posted Thursday night by 8 p.m., that exam, as you saw, hopefully you saw, or just raise your hand quickly. Did you see in the Google Classroom the thing that explains the exam? So I don't like, did anybody see in Google? Wait, just tell. Yes. Okay. Thank you, Christopher. That's good enough for you. Thank you, Allison. Okay. Thank you, Toiba. Okay. So I won't insult your intelligence by reading it out loud, but you get the bottom line. It will be posted Thursday night. It would be due back midnight by Sunday night. That is a strict deadline. We're going to talk more about that, but that's real. That's real. It's an exam. What you do to do the exam is anything you want. Like, there's no such thing as cheating. Like, since all kinds of cheating that you can think of are allowed, therefore they're not cheating. And I'll explain that too, maybe tomorrow. But you could do whatever you want to do that exam. But when you finally do it, and I would suggest doing a rough draft first, but then when you finally do a final draft, part of your job and part of what you're practicing in these homeworks, your job in your final draft of that exam is to make everything as clear and comprehensive and persuasive and eye-catching and easy, appealing to read. You want to give me a document that I want to look at, that is easy for me to follow, that is appealing for me to look at, where you clearly are like, this is question one. This is the deal. This is my picture. This is the stuff I did. This is verbal commentary over here explaining my steps. This is a different color over here showing that I really know what I'm doing. Blah, 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 blah. Your job is to make a well-presented document. Some of you on homework, I've even said things like, please skip lines between problems or something. You probably think that's super annoying that I'm saying that. I'm trying to encourage you to do things now that will make it easier on me by the time you get to the exam. Presentation does matter. You don't want me to take any more time on your exam than any other student. I mean, I'm sure you want me to like your exam more than, but you get my point. Okay. It's like practice for a poster presentation or whatever. So anyway, that thing is due midnight by Sunday. By the time you do it, you're only writing things down that you understand. You're going to great pains to show me that by the time you write them down, you understand them, blah, 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 blah. You're turning that thing in on time as one file. What will happen is, as it says in Google Classroom, on Wednesday, but directly prior to Wednesday, you'll get a document that will be very similar to the real thing, and it won't come with answers, but it'll be really similar. So it's like sneak peek at the real thing. Then you're all going to sit in lab, and first you're going to practice it on your own to really see on your own what you know, what you don't. You can have open notes and all that, but you're going to try to deal with it on your own and see like what your experience is like. Then about midway through the lab or so, Professor Talley will tell you, and then you can all help each other. So it's not that we're giving you a million solutions. We'll give you some solutions, but the real thing is we're giving you all this advanced time to like get your heads together and work through it before, and then the real thing will drop, will be posted Thursday night. The real thing will be not identical to, but very similar to whatever you practiced on Wednesday. We'll change things where we have directly given you answers. We'll change them slightly. We won't change things where we didn't give you answers. Certainly the structure, the instructions, the format, all that will be the same. We don't try to surprise you. That isn't the idea. The idea is to get you to know this physics. Okay, sorry. So anyway, that last thing on this. So that's like the deal of it. I will explain more tomorrow. Then Wednesday's class, we're not going to review much in class. That will be mostly what you do in lab, the way I just described. Wednesday's class, I'm going to warn you right now too, will be slightly strange. There will be some asynchronous, for independent reasons that have nothing to do with the exam, just by a bad coincidence on my side. Wednesday will be partly synchronous and partly asynchronous, or partly shortened, just because there's conflict on my side. I'll explain that better tomorrow. I'll warn you, but just be warned that Wednesday won't be a full period of synchronous engagement. Your review and your ability to prepare will mostly come from me tomorrow, and will come for Professor Talley. Okay, I think that's, I'm going to look in the chat. But last thing, when I say deadlines are strict for exams, and I do mean this, that doesn't mean that you don't sometimes have individual circumstances or medical or family emergency, stuff like that. If you anticipate that you're going to have an issue with Sunday night, midnight, the thing has to be returned to me via Google Classroom by midnight Sunday. If you start anticipating that there's going to be a real issue in your life, reach out and communicate to me personally. I can deal with personal situations. I can make personal accommodations. I have, and I do, and I will. But the more you want me to accommodate them, and the more you want me to be understanding of a personal circumstance, I just ask that you communicate in advance. The thing you don't want to do is just not turn something in at 11:59 without any warning. Like, that's bad for an exam. That has consequences. Okay, all right, I think that's clear. But if you have an issue, let me know in advance. And if it's a personal issue, that doesn't mean you have to divulge personal details to me. Or even if it's medical, it doesn't mean you have to prove it. It just means you have to communicate in advance, and we make a plan together. And if it's you during the midterm, it'll happen to somebody else on the final, or vice versa. Like, that can happen, but you have to communicate with me. I just don't want to be surprised. Okay, I'm looking at the chat, and I'm going to move on to physics now. Okay, oh, great question. Okay, wait, it is? Wait. Oh, okay, hold on, sorry. Oh my God, okay, apparently a lot of people, and I'm assuming all these yeses are about Tom Nook, okay, who's a controversial character, of course. Okay, but great. Okay, wait, hold on, there's something in the, oh, sorry, there are things in the person, give me a moment, I apologize, there are things in the direct chat. Give me a second, and then I'll get back to the 1 second. Sorry, bear with me for a second. Okay, okay, back to, I don't even know what's happening with the screen sharing here. Okay. I do have to get to, and then, what will the exam cover? That's a very fair question, because it seems like we haven't done anything yet, I know. It will cover, well, the overarching thing, it won't cover a lot. I mean, but we have to have an exam. The bottom line is simple harmonic oscillation. It'll cover simple harmonic oscillation, which is the overarching description of what we've been doing so far. But I will be more clear and explicit about I'll be more explicit about that by the end of tomorrow, when we will have done 3 more hours, like 4 more hours worth of material. But I'll really answer that question when you see the practice document. That's part of the purpose of the practice document. But it'll cover oscillation and this cosine solution to this differential equation, which is what we're going to get more in detail into right now. But yeah, I'll be more clear about that tomorrow, I guess, is the fast answer. But that's a fair question. Just bear with me and you'll see. It is, oh, well, okay. A lot of people think that's, okay. So yes, it's a very fair question. So, well, I could be more specific then, since we're about to start rolling with homework 2 now, and you're going to see how homework 2 helps us out with the last question of homework 1. It actually covers a lot. It will cover homework 1 and half of homework 2, not all of homework 2, but half of it. And you'll see, if you haven't already, that homework 3, which is posted, but I don't think I've put a date on it yet. I will put the date on it. I think officially homework 3 will be not due tomorrow, but due the next day. You will see that homework 3 is a lot shorter than homework 2. It's like 1 problem. In fact, I'm saying this to everybody right now, if you're listening, since not only was that a great question. Oh, wait, did the connection wait, can you not hear me right now? Hold on, I'm seeing hold on.
No, you're okay.
It's okay? Wait.
Yeah.
Okay. So let me back up for a second, since everybody's asking that question. Really, the exam will cover homework 1, half of homework 2, and homework 3, even though that sounds crazy, because you're going to see shortly, or you'll see when you look at it. Homework 3 is a 1-pager. It's a lot shorter than homework 2. And what homework 3 is 1 big practice problem of the 1 concept that really comes out of the last question of homework 1, and the 1 concept that we're going to sort of be grinding through or churning through today, and the 1 concept that you saw in lab like 2 days ago, the 1 concept of solving the differential equation for harmonic oscillation. Now, all these words I'm going to define in a few minutes, and I'm going to expand on this, but what I really want to say, I'm going to tell you right now that in most semesters, one of the problems on the midterm exam is literally just a reprint, with minor modifications of homework 3. Homework 3 is designed to be a practice problem for the exam. It doesn't make any sense until you get to it. But then when you get to it, you see that if you once you understand homework 3, you know something. And until you know that, homework 3 doesn't sound like so. And we're going to get to that tomorrow. I assure you, even if we haven't finished homework 2, we'll get to that tomorrow. So I guess my more concrete answer is all of homework 1, half of homework 2, and homework 3, pretty much, and lab is what the exam covers. Hold on, I'm going to say one more thing. Why do I keep saying it's not all of homework 2? Because some of homework 2 is about vectors, the dot product and the cross product, vector multiplication. Now, we did get into dot products a little bit last class. I did, but nonetheless, I can honestly tell you right now that the business of dot products versus cross products, that's not a focus of midterm 1. So we may not go, it's possible we won't go over those exercises before midterm 1. So every time I say half of homework 2, that's why I'm saying that. But all the business of cosines and derivatives and all of that, you do need for exam 1. So this will be more clear when I get rolling today, when I finish tomorrow. But all right, I'm going to go back to the chat and see. Also, sorry, I'm going to turn on my focus. Okay, hold on. I know we'll get to this. Okay, so let me get back to the chat. Okay, good. Right. Okay. Oh, it's sort of scary when everybody likes that question, but okay, hopefully I sort of answered. Loki happy. I forget what that means, but okay. 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 So I think we're on the same page now. All right. So let me get rolling here with. Okay. All right. So I'm going to go straight just to get this rolling. I'm going to go straight now. Well, this is a summary of what's going to happen today right here. Let's try to do that. We're going to try to cover the relationship among these 3 equations today. That's the focus. Hopefully, if you've been doing your homework, you see that this is related to homework 2 and homework 1. I'm going to start it. We're going to start going straight to homework 2 right now.
But we didn't even finish homework 1 though.
Right, no, but that's what I've been saying. Right, I want to say we're going to go back to the end of homework 1. I want to. That's what I've been saying. Wait. Oh, I did put a due. Oh, sorry. Hold on a second. Keep that. But yes, we're going to go back to. I think we gave an answer to homework 1 to the last one. I'm going to go back in a few minutes. I want to do a couple of exercises from homework 2 just to keep going forward. But I think, and also to set a context. But then I promise I'm going to go back to the last question of homework 1. Oh, I put a due. Okay, someone put in the direct chat. Hold on, I'm going to change right now the due date for homework 3. We can change that to Wednesday. Hold on. Okay. You're right. Thank you, direct chat person. You should definitely submit that report. Okay, I'm going to change that though. Okay, well, and all right, if maybe I'm confusing people. All right, I will. All right, maybe I'm being confusing. I'm not going to take a vote. I'm going to just assume from the one person that just spoke about this. Wait. Wow, Evelyn is really all over the multiple. Okay. Wait, I'm going to take that. Okay, hold on one second. Fine. I know I got to get rolling here, but okay. First of all, I'm changing my mind in light of 2 people that just wrote in the chat. I will go back to homework 1B right now, so we're organized. But we will get to homework 2. I'm going to go right back to this thing. And yes, to answer Evelyn's question, yes, he can. Okay, and so can you, I guess. Okay. Question 6 of homework 1. So this is homework 1 now, homework 1B. Question 6 was, at t equals 1, what is x, right? That was the question. Now, the first thing, I'm going to change the first thing I said, and I'm saying right now about that is really, to a physicist, that is a little bit of a disguise on a question. It says at t equals 1, what is x? So that we can picture something concrete and specific. So we can we think we're answering the question, where is the mass at the first second of this experiment? But honestly, we would be able to answer that question if we had an equation, right? Or a function, if we had an expression that linked x to t, if we had some equation that treated x as the dependent variable and treated t as the independent variable, then we could just plug in 1 for t and it would spit out x and we'd be done, right? So this is one of those times where when you're sort of first doing physics, you might, or question 9, I'm sorry, okay, thank you, that's a correction. There's a, got to open a portal for that. Sorry, question 9, you're absolutely right. Thank you, and you should please submit for points for that. I need to open a portal for correcting the spazzy professor. Thank you. Yes, that's question 9. What you might think, what people tend to think at the beginning of physics is like, oh, okay, so what's the xt formula? I need to, is there an equation sheet? Like, can I look up in the textbook? Can I go on? But once you start really getting into real physics, it's not about looking up a pre-existing equation or a pre-existing formula in order to then do the question, because then it's really, then it would just be a math question. What's a physics question about this is it's actually our job based on the situation to develop a relationship, an expression, a function that will capture this situation. So what I'm saying is, and this is what we want to get used to as physics goes on into deeper and deeper levels, and especially in the lab, if you may have already noticed, the actual thing that you're trying to get to by the end of every physics lab is you're not testing an equation, you're not plugging in from an equation or into an equation, you're trying to develop a new equation from your data in a lab. And that's where, so that's what we're trying to do here. So the real question, so I'm backing up now. I'm starting from the beginning. I'm slowing it down slightly. What our real question The real question here is, what is x as a function of t, given this situation? Like, you can't say, so we're not, so this is why you can't even look in a textbook. I mean, of course you could, but it's not even just like, what is the xt equation? There's a million different xt equations in physics. All of physics is about xt equations. One big one that you learned last semester was x equals 1f at squared plus b naught t. That is an equation that assumes a condition or a constraint called constant acceleration, right? But that's not the condition that we have here. So what we have here, given that a is not a constant, specifically what we have here, like we said on Friday, last Wednesday, what we have here is that f equals negative kx, and of course always f equals ma, right? This is the given. I mean, f always equals ma, but the given here is that the f depends on x linearly. Therefore, a is not constant. It depends on x linearly, right? So, and I know I'm just reviewing or expanding what we said last class, but the GDP here really is f equals negative kx and f equals ma, f net equals ma. Also, I'll just write it here, just like we said last time. Another GDP, here, let me be very clear. Like, this is a GDP, this is a GDP. These are general definitions or principles that we need to solve this problem. But another one, another GDP that we need for this problem that's always been true and sort of got reinforced in the prior question, in question 8, I think it was, right? But we never really maybe cared about before, but it's always been true, is that by instantaneous acceleration, by definition, what we mean is second derivative of position with respect to time, right? So these are our three GDPs that we're going to use for this problem. Note again, a GDP is something that was true even before you walked into the problem, but you might not have cared about until this problem. Like A equals d2x dt squared. That's been true for every single thing we've done on this entire sheet. But now we care about it. Like now, and that's why it's important to list GDPs. Like they're all obvious, but they're not all obviously fruitful for any given circumstance. Okay, wait, I'm just looking at the chat, but I'm going to go to the next page. I know this is still technically, I'm just restating or reviewing what I started to establish last Wednesday, but then I'm going to put these things together a little bit more slowly and thoroughly than I did last Wednesday. Again, this is, I'm completing homework 1 by popular demand, but there's something in the chat. Hold on. Something in the chat. Sorry, yes, this is question 9. Yes, this is question 9. Someone did correct that, but yeah, for all, yes, sorry, I originally said 6, but I'm just looking in the chat. Oh, okay, I'm backwards in the chat. Yes, question 9, thank you. And anybody who corrected me on that, especially since a lot of people did it politely in the direct chat, which I appreciate, definitely submit that for points. Okay, so we have this here. So what we said last Wednesday, we said, okay, let's start putting these GDPs together. And let's note then that negative kx equals m a, so negative kx equals m d2x and by the way, if you put something in the chat and I ignored it today, it's not on purpose. So please, if you put something in the chat and I never got to it, please put it in again now, because I think that I did. But it just occurred to me there's at least one name in my mind of one person who sent something, and I don't know that I ever. So it wouldn't be rude. If I have ignored you in the chat, it's not on purpose. Please remind me again, whether it's private or public. But okay, so we have this. So now I'm going to rearrange this slightly. And say this. Okay. Now, we got this far last Wednesday, and then I rushed at the end and I proposed a solution for X that solves this, but I did that very fast. I told you what the equation is, but I didn't tell you where I got it or why it was true or anything like that. So okay, so let's slow down right here. Okay, let's ponder this for a moment. And again, we're going to ponder this for a moment in its own terms, but it is ultimately what homework 2 is trying to show you from a different perspective, or well, the beginning of homework 2. And it is in a way what the first couple of labs were trying to show you from a different perspective. What we have here, we have physics brought us to this math equation. Physics laws said that we have a situation where d2x over dt squared equals negative k over m x. Like I just rearranged it. I rearranged it on purpose, sort of in a typical math or physics style. I rearranged it to get the derivative all by itself, and then to get the variable by itself on the other side with a bunch of constants collected before the variable. That's just a style thing. Like, you know, you could write it any way you want. But the key point here is that the derivative is sitting there, the second derivative is sitting there by itself on one side. This is saying, so physics brought us to this point, but this is now a math equation. This is a, well, I'll just say it. I mean, what this is called a differential equation. This particular math expression is called a differential equation. In fact, if you want to be technical or whatever, it's actually called a second order differential equation, because the kind of derivative that it's talking about is a second derivative. Okay, now, first let me say again, I always say, it's a very important piece of mathematics. Like this is a math challenge that we have to solve now. Physics brought us to this point where we now have to do some math unpacking. Now now in no way do I expect, nor am I requiring that anybody's ever, there are classes in the world called differential equation classes. I mean, I've taken a number of them. You were not supposed to have taken a class called differential equations before you took this one. Like maybe you did, some of you, but it was definitely not expected. It was definitely not required. You might be intimidated hearing this term or looking at it. I understand that, but please don't be, or please don't think you're in the wrong place. The reason you were not supposed to have done this math before you got to this physics is the same reason you weren't supposed to have these lectures before you got to the lab. This is a science class. Physics, in the history of physics, physicists were like Hooke and Newton were doing things with physics and figuring things out with physics and putting physics laws together, and then it brought them to mathematical relations, which then they had to discover or work through the math to figure out. A lot of math that gets invented or taught in math classes came about because it was figured out in a physics context. And that's what we're doing here. Sometimes for some people, it is thought that the more math you have in your background before you take a physics class, the better off you are. Some people think that, honestly, and I understand that. But honestly, it's just as likely for many of us, definitely including me and maybe many of you, it's very likely for many of us that we don't really appreciate or understand math until we start seeing it come alive and be motivated in a physics context. It's just as possible that physics courses should be required before math courses as the other way around. So all of which is just to say, I'm not expecting that you've ever seen this before. Not at all. I'm expecting that, like all physicists in time, you can join with me together and look at this thing and say, okay, what this thing is saying, what this equation is saying. Well, first of all, this is an equation to unpack. It is not an answer. It poses a question. This is a differential equation because it says, it doesn't tell us how X depends on T. That's what we want. We want an expression where T is the input and it spits out X as the output, right? We want an expression that directly links the independent variable. I'm going to write this again on the next page. We seek an expression which directly links the independent variable T to the dependent variable X. That's what we want. This thing that we're looking at here, what we're looking at so far from physics, right? Not from math, from physics, we have this thing, I'm just rewriting it. that says, it doesn't say you plug in T, you get out a certain X. What it says is that if you take, what it says is if you take the second derivative, the derivative of X with respect to T, if you take the derivative of the time derivative of X, what it says is you get back X times a constant over a constant, which is just to say a constant, times -1, right? That's what this thing says. Now, notice, it does contain all the information that we want. It is treating, you can tell by the way the derivative is written, with X in the numerator and T in the denominator, you can tell that this thing is treating X as dependent and T as independent. So that's good. Like what we have here is consistent with what we're looking for, but it's not the same package. What this thing says, you're saying, I want to know if I plug in T, what's X? This thing is saying, well, I don't know, but I do know this. Whenever you eventually get X, if you take the derivative of it twice, you're going to get back X times a constant times -1. So we're saying, well, I mean, that's great, but like, so what? Like, how does that tell me? How does that tell me at T equals 1 what X is, right? So we have to unpack this. This has to be solved. Okay. Well, I'm just trying to say, so what I wrote here, a differential equation by definition expresses some derivative as a function of the dependent variable. That's the key. A differential equation, just quickly to say this, a differential equation is not just any equation with a derivative in it. It's more than that. A differential equation is not just an equation with a derivative in it. A differential equation is one that it relates a derivative or expresses the derivative as a function of the dependent variable. That's the twist. That's the weird thing about differential equations. I'm going to say more and more about that as time goes on, but please remember here, time is the independent variable. Position is the dependent variable, okay? If we had a situation here that just said the derivative of the derivative of position is like if we just said the derivative of the derivative of position, yeah, if we just said like the derivative of the derivative of position is like 9.8 meters per second per every second that the thing is moving, right? Like gravity, right? Like if we just said, oh, the rate of change and the rate of change of position with respect to time is this function of time, like the thing is speeding up by 9.8 meters per second every second, then that would be like old physics. That would be like, oh, right. Oh my God, exactly. Sorry, person in direct chat. That's awesome. That's exactly, okay, I'm going to, okay. I didn't, yes. All right, so someone in the direct chat just wrote, wait, so you couldn't take the antiderivative twice to find the function we want? That person exactly nailed exactly what I was nervously about to say. And I'm going to repeat it. Whether you understood what she or he said, like she or he is right. So let me say again, right. If we had a derivative or a second derivative or any kind of derivative expressed as a function of the independent variable, if we had an example like, well, the thing gains velocity, like it's accelerating at this rate, the rate is that it gains 9.8 meters per second every second, then even though that sounds complicated because we were just given a derivative rather than a position, we could take the antiderivative of that, and then we could do it again. And then we could do it again because it's two derivatives, and we would eventually get to the thing we want, position. And that's in effect what you were doing all first semester, whether you thought of it that way or not. Like the reason that we developed all these equations from constant accelerations and things like that is because in effect we were being given derivatives as a function of time in physics 203. We were being given information about rates of change as they related to the independent variable of time. So in effect, you could unwind those things. You could take antiderivatives, or even what many of you know to be integrals, and you could solve that way. Or one person could take the antiderivative or the integral like once and get a new equation. In other words, yes, the antiderivative of A equals, excuse me, the antiderivative of V equals AT plus V naught is x equals 1/2 AT squared plus V naught T. I know that just clicked with some of you, and with some of you it did whatever. I'm just saying, like, the equation that you had, x equals 1/2 AT squared plus V naught T, was the result of somebody taking an antiderivative of V equals AT plus V naught, which is just a rearrangement of A equals V minus V naught over T, whatever, and then doing it again. Exactly what direct chat person just said. So in the old days, we could just take antiderivatives or integrals, or even if we didn't know that's what the teacher was doing, that's what the teacher was doing when they developed constant acceleration equations for us, and then we used them and we moved on with our lives. But exactly what I'm saying right here is, oh no, this is a trickier thing. This is a more interesting thing now, because the second derivative here, the acceleration, d2x over dt squared, is not being expressed as a function of time. It's being expressed as a function of position. So exactly right that here, we got to do something. We got to solve this thing, but we can't just unpack it by doing derivatives backward because it's not being related to the independent variable. I mean, like, I'm kind of excited because that's what I was going to say anyway, but I'm kind of excited that someone just said it in chat even before I could. Okay, wait. So, yes. Okay, wait. There's something else in direct chat now. Hold on. Sorry, hold on one sec. Hold on, I'm just responding in direct chat. But yes, that's very good direct chat, Bert. Like really good. Whoa, hello. Okay. Hold on. I'm just catching up to chat, and maybe you're catching up to me. But that's so. Wait, I'm going to catch up to chat in a second. But if I'm losing some of you or just boring some of you, which I understand, the upshot of what I'm saying right now. The upshot of what I'm saying right now is I'm not trying to intimidate anybody or lose anybody. I'm trying to say the physics just brought us to an equation that we have not solved before, a type of equation that we haven't even solved before. It doesn't mean we can't. It doesn't mean we need a whole new class in order to solve it. It does mean we need to be familiar enough with regular calculus to see the subtlety of this, to see that this isn't just straight up, that our regular old techniques of antiderivative or integrals won't directly work here. I do want everybody to see that. I want you to see why we have to do something else to unpack this. All I've said so far in this class right now is this is an interesting equation that will require a new type of thought to unpack. We will do the new thought right now, and you sort of did it in lab and blah, blah, blah. It's not unfair thought, but it's new thought. That's all I'm saying right now, but I'm responding to the direct chat. Hang on one second. Hold on one second. Okay. Hold on. Okay. Okay. So what are we going to do? All right. Well, a lot of you may recall with antiderivatives, with integrals, they're not straightforward, right? They're more like, for most of us, derivatives, a lot of us, even if we don't totally understand what's going on with them, we can do them. A lot of us, there's rules you follow, there's an algorithm, there's a procedure, but you might have noticed with integrals, it's a little trickier. I mean, most of us find that integrals are a bigger leap than derivatives, because with integrals, it's more like puzzle solving, right? It's techniques and experience that there's no one clear path of algorithms or procedures that you follow just to do an integral. Many integrals can't be solved at all. And when you look at an integral for the first time, you sort of have to decide what type of integral it is, and you have to play with it, and it comes from experience, right? Like, that's not an accident. That's not because your math teacher's being mean or something. It's because like integrals are they're not algorithmically solvable. Well, same thing here. There's many different ways to solve different differential equations. We're not here to solve all the differential equations in the world. We're here to be physicists and solve the ones that come out of physics and face us. And it turns out a lot of physics does revolve around these types of equations. So one method that physicists and mathematicians developed for solving these differential equations is that physicists and mathematicians got scientific about it. One of the ways that both physicists and mathematicians solve equations like this is with an experimental method. They conjecture and test and verify, i.e. they guess and check. I'm going to write that right now. In other words, these things come from experiment. That's why you do labs first. They come from experiment, and partly how we solve them is we experiment with different thoughts until a thought works. And luckily, we can tell whether a thought works or not. The proof is in the pudding. You'll see what I mean. But I'm saying, whoop. Oh, you can't hear me. Wait, can you? Oh, right. Sorry, I wasn't talking. I was writing something down, but can you hear me now? That's so funny. You can. Okay, cool. And Penny. Okay. Okay. So I'm going to say this part a little defensively. I always say this. I'm about to solve this differential equation for you, or show you a solution to it. I'm going to literally do what you might call guess and check. educated guess and check. If you want to be more fancy, I'm going to call it conjecture and verify. I'm going to build a guess as to the solution to this. The guess comes from experience and lab data or lab experience, because this is a scientific process. And then I'm going to check whether that guess is right or wrong. Before I go any further, it might seem to some of you like, well, wait, that's not like really mathematical. You're just going to guess and check. Like, what's up with that? What do real math people do? This is what real math people do. It is really mathematical to guess and check. And it's certainly scientific to guess and check for a couple of reasons. One, it's not a random guess. I mean, it's going to be a guess based on lab data and lab experience. But number two, well, there's really three things. Number two, with an equation of this kind, there's literally no other way to solve it other than writing a computer program, which still ultimately would be doing an exotic version of the same thing. There's literally, to this day, even if you're a strict mathematician, there is no procedure, like linear procedure for, in other words, I'm not cheating you. I'm not condescending to you or something like that. I'm not tricking you. The way we solve certain puzzles is we get experience as to how to guess solutions to certain puzzles. And then what makes it true mathematics and true science? Well, number one is that we're actually not plugging and chugging. We're actually deriving original thought, i.e. we're doing science, we're not just mimicking it. But also what really makes it mathematical and scientific is that no matter where we get our guess from, no matter how good or random our guess might seem, we have a procedure to prove whether the guess is actually correct or not. The ultimate mathematics of this, and this is where homework 2 comes in, is I'm going to build a guess, like right now. I'm going to build a conjecture that I hope you'll find persuasive or reasonable, and that you have the same equipment to build. But what will really make it math is that once I build that guess, I'll be able to literally test whether it's exactly right or exactly wrong, because I'll take derivatives. And I'm also going to say, finally, I'm about to do that. You're not going to have to go through all of this every single time. I'm going to try to convince you right now from this guess what the solution to this differential equation is. You're not going to have to reinvent the wheel every time. This differential equation will come up enough for the rest of your life in physics that once you understand or accept, or once you can follow how I got this solution, then that's the solution you're going to use. You're not going to have to reinvent your own to a million different things every time for whatever it's worth. So here we go. Here's what I mean. Terrible. Sorry. Right. Okay. Now, remember again. Remember what's really. Oh, sorry. Oh no. Wait. Sorry. Evelyn's question. Very good. That question might be coming from some deep mathematical experience on your part. In this context, in physics, or well, certainly in this context now, certainly in this midterm exam or final, I won't ask you for all solutions. I will ask you for a solution. Partly that is because we're a physicist, not a mathematician. So we have to come up with a solution that works, that can make predictions and that can make predictions. Like we ultimately want to know. Ultimately, we want to know at time equals 1 second, for example, where's the mass? As long as I come up with an expression that can get me that information, that's what I want. You are right. There could be more than one way to skin that cat. I'm not now, and I won't be asking you for all the possible ways. As a scientist, I'm asking you for a way to predict position as a function of time. So I mean so Evelyn's question is a very good one, but that's my answer. Oh, and also my drawing is terrible. Hold on 1 second. I mean, it's not terrible, but it's not symmetric. Okay, that's better. Okay. So the first thing I'm going to say, and maybe you might want to tell me, Evelyn, if that were, well, anyway. So the first thing I want, and everybody's got to remember now, this is a little tricky. What's tricky about this is not that you haven't seen, it doesn't matter if you've never seen this before in a math class. I expect that you have not. What's tricky is that we're going backwards. This is like reverse engineering. Please remember our goal, and this is also, again, why it's really good practice to always do step 2, WIQ. Like, what is the question here? Honestly, the question is, what is X as a function of T? We are not looking up in our book to find a formula that relates X to T and then plugging in. No, we are trying. The actual goal of this question is to derive a relationship between X and T. And again, let me say to everybody, even if you think you already know because you had the labs already, or because you worked on this homework and you already went on the internet and you, like, even if you think you know the answer, I'm here as a teacher trying to show you how do you get to this answer. The answer we're looking for is going to be some expression, some function of T that yields X. I'll say even one more time. That means we're going to get an expression that has a bunch of letters in it that are constants, or in a bunch of numbers that are constants maybe, but that the only independent variable in it is T, and the only dependent variable isolated by itself on the left side will be X. That's what we're looking for. The information we have is this information about derivatives, and we're trying to go backwards and unpack those. So what do I say to myself? As a physicist, is, oh, I was in the lab and I was watching masses go back and forth on springs for a while. And I noticed that if I let a mass go back and forth on a spring for a while, what it does is it goes back and forth for a while. Like, if I picture a graph that treats T as the independent variable and treats X as the dependent variable, right? Like, and remember now, like back and forth for a horizontal spring, or even up and down for a spring, if that's what your first lab was, I guess, like up and down in space. Once we add the time element to a graph like this, then what, in a graph where time is on one axis and positions on the other, what we get is this thing that's smoothly curving back and forth for a while, right? Like, for example, what I'm trying to say, I mean, I'm saying this picture here is the simplest possible depiction of what it would look like for a mass to go back and forth between some initial position X naught and some symmetric position on the other side, negative X naught, right? Whether that X naught was 15 centimeters or whatever. This is what the graph would look like if we took a bunch of data every millisecond of where the mass was. We would get a curve that's going up and down smoothly like this. This is the simplest possible. Like, if our data were really good, we would get a smooth, symmetric, patterned, periodic function like this. We wouldn't get anything any simpler. Like, even if our data were really good, we would not get, just to be clear, we would not get something like this. Like, that's even simpler, but that's too simple, right? Too simple. We wouldn't get a sawtooth because the mass does not go at constant velocity toward one position and then instantaneously grind to a halt like a cartoon character, and then instantaneously, in no time at all, turn around and start going at constant velocity in the other direction, and then do that, right? Like, a sawtooth is too simple. That's not what happens. We have something that's speeding up and speeding up. Sorry. We have something that, is speeding up and speeding up and speeding up as it goes toward equilibrium, and then slowing down as it heads toward the other amplitude position, and then speeding up and speeding up, right? Just like we were asked in question 8, we have something where the velocity is going one way while the acceleration is going the other, but then the acceleration changes the other way, so there's a jerk that's going the other. Like, we have something that's smoothly running through all of its derivatives back and forth as it goes back and forth. So we would have a curve that's continuous and smooth like this. And the curve would start not at 0, 0, right? It's the y-intercept would be, the first point would be 0, x naught, not 0, 0, right? So what do we have here? Now, I'm not proving it. I'm looking at this. I walked out of the lab. This is my XT data. So I think to myself, oh, okay, that looks like a cosine graph, right? I have to have some math and science experience to make that recognition, but this is really what we do in the lab. We get a bunch of data. We first ask ourselves, what's the basic shape that the most simple shape I can think of that basically captures that relationship. And the basic shape is not y equals x squared. It's not a parabola, right? It's not y equals x cubed. It's not a cubic. It's certainly not y equals x. It's not a straight line. It's not y equals sine of x because it didn't start at 0, 0, but it does look very much to me like some kind of y equal, or yeah, some, not y. I mean, it's not x equals t. It's not a straight line. It's not x equals t squared. It's not a parabola, blah, 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 blah. But it's some kind of x equals some kind of cosine of t, right? If I just look at what happened in the lab, or just look in my mind at what would happen in the lab, in a good lab, I realize that x equals some kind of cosine of t. Now, let me write that more neatly. I'm saying some kind. I'm saying the basic shape here is some kind of cosine of t, but I'm putting some blank spaces before the cosine term and right before the t, like in other words, right after the cosine term. I'm leaving some space because I don't know the details of this yet. What I know is what I'm conjecturing is the basic shape, that it's some kind of cosine. Now, also, again, in answer to, I think it was Evelyn's question, could other things maybe describe this too? Could I like maybe describe this as like a sine of t, like plus or minus like pi over 2 or something? Yes, probably. There are probably other ways I could describe this, but the simplest one that comes to my mind, if I'm looking for something where I would plug in t and it would spit out x, as a scientist, I'm always looking for the simplest possible way to describe the data in front of me. The simplest possible way I can think of so far is some kind of cosine. But what would be too simple? It would be too simple if I literally just said x equals cosine of t. That would be too simple. And I will tell you why. Or maybe you could tell me why in the chat. Like it is, cosine's a basic shape. But if I literally just wrote too simple, sorry, if I literally just wrote x equals cosine of t, no, that's too simple. I'll tell you why.
Wait,
Oh, I'm sorry.
listen.
Yeah.
If when we're dealing with differential equations, you said we can retrace back, and like if it's in terms of the not time, the dependent, right? Can we find the derivative to go back in a sense?
No, right. That's a good question. But if I'm understanding you correctly, it's a good question. It's like a super important question, but the answer is no.
Okay.
And I don't mean that obnoxiously, but like because okay, let me just turn back a page. This is like a really important thing. And honestly, this threw me off for years. It's like super important. I may have to say it more than one time, but where I'm going back, if this is the equation that in blue at the bottom of the page, what I want to say like to you and to everybody is this x over here, the blue x, if that x were a t, if that were just a t, then this entire class that like basically
Yeah,
then
we could have basically just found the integral if it was a t, because it would be the independent variable, right?
100% correct. Yes.
Okay.
Yeah. No, and that's great. And honestly, to everybody, this is like a very delicate thing. When you guys were asking, like, an hour ago, like what's on the first midterm or whatever, I don't mean to be weird, but honestly, what I'm doing right now is the first mid. If this letter right there this is in agreement with what Christopher's saying. It's also in agreement with what someone in the direct chat said like 20 minutes ago. But the more of you that can see this, the better off we'll all be. if that blue letter at the bottom of the page were a T, not only would we all know what to do, but in effect, that would be physics 203, and no sarcasm intended, we wouldn't have a first midterm. Like all of the first midterm, in effect, is what do we do when that thing is an X rather than a T? And that's everything that I'm talking about right now. And the first thing that everybody has to,
No, I was saying I'm kind of glad you kind of went through this, because I was kind of discussing somewhat about homework 3, and I just went back to look and I realized that it's in terms of the dependent variable, and I was thinking probably I could have used the antiderivative, but now I realize it's in terms of dependence, so I can't. So
that's awesome. Like seriously awesome to you and the other direct type person, and to everybody else. Let me say again, and I'm not being polite to these guys. I mean, I'm telling you, it took me years. I would have saved myself. It took me years to realize this distinction, like really. So for anybody who's tuning in now or half catching what they're saying or have not, the thing is, I still, both to Christopher and the direct type person, I still haven't finished explaining to you what to do. And that's why to some of you now, I get it, if you're thinking like, oh my God, he's taking so long. Like, can he just give us the answer? Why is he spending so much time on this? Like, I thought we were up to homework 2 already, or blah, 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 blah. Like, I get it. I'm sympathetic. But the thing I have to tell all of you is the reason I have to spend this long on showing you what to do is that you first have to see why there's an issue. Like, it seems like we could just take 2 antiderivatives. But we literally can't, because this thing is an X, not a T. And because it's an X, not a T, what we actually have to do, in effect, is guess and check, which makes a lot of people uneasy because they're like, that doesn't seem like science or math. But I also just, again, want to tell everybody, actually, it's more real science. The real science and math, the reason people can still get jobs, the reason that there's still things to do in science and math is because there's still a whole frontier of stuff that we don't have equations for yet. That the way we get them is we guess and check. Our guesses are super educated. So that's why we spend all this time in school, because like we can't just guess from nowhere. But then because it's math and science, there's mechanisms for checking and then finding out when we're right at the end of the day. But the reason one person gets a job and another person doesn't is because of how good they are at the art of science, which is the art of educated guessing, right? Like, so, okay, so anyway, at least 2 people in the room at least get the issue here is we cannot just take antiderivatives. What we literally have, actually, I'm going to say is one, so we have a differential equation. Again, also, I'm not saying you had to have taken differential equations to do this. In fact, it would be horrible if you did, probably. It would just like cloud your brain. But I am saying you have to respect the fact that we're doing something new now. That's why this is a class. Like, so what I'm saying is we're looking for, we're looking for a function, like everybody. And I'm psyched. If I sound angry, I'm just excited. Really. To everybody, we're looking for an X. We're looking for an X such that when you differentiate X twice, you get back X itself times a constant times -1. That's a very weird question. I'm going to keep saying it because I don't want you to be intimidated by it, but I want you to respect it. We're going backwards. We're not now learning how to differentiate X twice. We're looking for an X such that when you differentiate it twice, it gets back itself, like times a constant times -1. And okay, so we have to like think what could possibly be an X that could possibly do that. So we think about the mass going back and forth on the spring in time, and we think, oh, that looks like a cosine function. So let's try a cosine function. You'll see what I mean in a moment about by trying. And also, let me say to everybody, I promise you, I mean, I've done this again, just to bear with me. I know this seems all nonlinear. I'll also say once we finally land this plane, once I finally show you this solution, then we move fast. Then we just use it a lot, and all of homework 3 just practices it. It's not going to be like this for every single class for the next 5 weeks. I know this is right, but we're trying to set up a new architecture. Once we set it up, then we'll live in the building and we'll do lots of things. But we have to set it up. So anyway, so we're thinking, okay, it's a cosine equation. Also, last thing too, at least 2 people are helping a lot by showing me that they're at least with me. You could put things in the direct chat that say that you're not with me. That would help in a different way. But the feedback is helpful. Anyway, I'm guessing a cosine function, some kind of cosine function, but it's too simple to say x equals, like this is too simple. I can't just say x equals cosine of t. Why? Because these are all measurements. T is a measurement in reality. X is a measurement in reality. T is measured in seconds. X is measured in meters. We actually have to, this is where units, they used to be a pain in our butt when we first took Chem 1.0, whatever. But now, actually, they're our friend. Actually, they're our friend. You cannot take the cosine of a second. It doesn't make any sense. You can't take the cosine of time. You can take the cosine of an angle. You specifically measured in, I'm going to say it, radians. You can take the cosine of radians. We have to, and for some of us, we're going to have to review what radians are. Some of us are not, but we definitely have to use them. You can only take the cosine of something measured in radians. You cannot, it doesn't literally make any sense to take the cosine of something measured in seconds. So that is why I'm putting a blank space before the t. I don't even know what's happening here. I just know there's gonna have to be some constant before the t whose units are radians per second. Right? If you think about, and again, tell me in the chat if you do buy this or not. We're building up a conjecture here. We're building it up from scientific and mathematical experience. What we're saying is x has got to be some kind of cosine of some kind of t, but it can't just be of t. You cannot take the cosine of a second. You could take the cosine of a radian. So we're going to have to multiply t by some number, something that doesn't change from, like, as the mass is going back and forth on the spring. Oh, very good. Hold on a second. I'm just going to respond to a direct chat here. Hold on a second. Hold on. Oh, and my son's coming to say, hold on, sorry. But wait. And direct chat person that I'm responding to right now, please submit that for points for the right or wrong portal. That's awesome that you just said that. And it's awesome that my son is feeling good and soon going to look us on. Oh my God, no, he's not going to. Oh, he's going to be outside. Okay. Yes. Oh, awesome. Sorry. Okay. Oh, things are, the chat light is light. Yeah. Oh, wow. And then people are liking each other. Oh my God, I totally have to open up a portal for this feedback that you're giving each other. But yes, this is awesome. All of you should submit for points, and some of you are going private, some of you are going public. It's fine either way. But I hope the people that went private now see how right they were, and that maybe they have nothing to be embarrassed about, like quite the reverse. So yes, but I'm agreeing with the public people. Awesome. Wow, this is like a class. Doesn't it almost feel like a class? So yes, okay. So, and I'm gonna get to, so I totally agree. Again, those of you who are not following the chat, it's okay. Don't worry about it yet. But well, maybe. Wow. Remind me of that. Sorry, I'm assuming you can all see the chat, so I'm not reading it out loud. But yeah, okay. Awesome. Okay. All right, we're about to be interrupted. Oh, now he's bringing it up. Really? Like, do you guys remember what it's like to be 8? It's no picnic. Hold on. Okay, but I love you. Please stop. If you, in an hour, we'll do this on, but I gotta keep. Thank you.
I'm not gonna wait.
Well, yeah. Okay. Well, then you're not gonna do well. Okay. Okay. Yes. Wait. Okay. So. I'm just trying to get my thoughts together. Okay, actually, good. Since you've been in the lab and you guys are all being awesome, let me deal with that right now. Yes, you are correct. So yes, like there's got to be some constant that goes next to the t, that goes before the t. Like if I knew nothing, I just know there has to be something measured in radians per second so that the seconds get canceled out and we're left with radians, right? But then I think about it the way you guys are thinking about it. I think about what I know about cosines. I think about cycles. I think about the lab, and I realize, oh yes, I realize what you're telling me. I realize. Well, side note too, and you might want to put this in your notes, even though I'm not going to. Whenever I use square brackets from now on, if I ever use square brackets, I'm talking about units when I use square brackets. So like, I wasn't saying that the constant equals radian per second, but I'm saying like it has to be measured in radians per second, right? So Okay, this is illegible. I should actually, no, I'm just going to copy this on the next page because this is important enough that I was going to go in a slightly different order, but I like the way you guys are doing it. So let's stick with that. Let me just recopy this on the next page. We're saying so far. Okay, I'm going to say a bunch about this right now. Cool. So first of all, yes. So this has to be in radians per second. We can call whatever we want, right? We can call it B. We can call it like we can give it any letter we want as a name for this radians per second thing, and I will in a minute. And I know you already know the letter. It sounds like, but even before we give it a name, let's not let the name confuse us. If it's a constant, and it's measured in radians per second. So it's some kind of rate, right? Just like velocity is measured in meters per second, it's a rate of displacement space per time. Well, this is not meters per second, right? This is radians per second. So it's a rate, but it's a rate of radians. Okay, radians are some kind of angle. That's weird. I don't know where angles are coming into this. I will explain in a moment. But this is a rate at which angles, radians, are completed per time. So it's not a velocity, it's not space per time, it's completion of some kind of angle per time. So yes, we call it an angular frequency. That may or may not explain what it is, but that's what we call it, angular frequency. And the letter that we designate for it is a letter like V for velocity, but it's not V. It's sort of it's the Greek lowercase letter omega, right? And yes, we use, as I think you know from lab, we use from now on omega to stand for angular frequency. Now we could have used any letter. Again, we have to be careful here. We're reverse engineering something now. So even though I'm assuming now, or I'm gathering from the chat that you have some comfort with this from lab, we're not assuming that we already have equations. We're not assuming we already have equations about omega, or that or something like that, or that we had a whole chapter on omega in physics 203. We're just using the letter omega to stand for this concept that seems to be popping up, known as angular frequency, the frequency at which we sweep out angles. Now, whoa, before I go any further, since you're already telling me that you know it's angular frequency, this definitely used to confuse me. It may confuse some of you. And more to the point, it may unconsciously confuse some of you without you even knowing you're being confused. Let's remember, we're talking about a mass going back and forth in a straight line on a spring, or maybe in your first time, a mass going back and forth in a straight line on a spring. So it's very reasonable for us to pause for a second and ask the question, where the heck did angles come into this? Why are there angles at all? Like, what do radians have anything to do with something going back and forth? Very good question. I would like to answer that. First, I'm going to look in the chat. Something is on the chat. Wait. All right. Oh, okay. Wait. So things are happening in the chat. Okay. Let me try to. Good questions in the chat. one's more on the topic than the other. Hang on one second. Let me just try to answer the direct chat. Oh, wait, did I do? Okay. Okay. Right. So there's a good question in the direct chat. I'm not going to read. I'm going to read the question. That's it. Okay. There's a question in the chat that says, "Why is a spring considered angular motion if it's in simple harmonic? If it's in simple harmonic motion?" Yeah, good question. That's exactly my point. Like, let's establish that right now. What do angles have to do with something going back and forth and back and forth? Here's one. Okay, I'm going to say this to everybody, not just, once again, I'm really glad that at least one person in the class asked exactly the right question, which is what I just read. Why is this considered angular motion if it's in simple harmonic motion? I mean, if the thing is going back and forth, I'm glad one person asked that, but let me tell you all that I would be explaining this right now to all of you, whether or not someone asked that, because it is the right question. So let me say very definitively to you all, for starters, an angle is not this. We all think that. I mean, I used to think that. I used to think an angle was an intersection between two lines. I mean, that's one way to think about it. It's not the helpful way to think about an angle. What an angle is. Wait. Yeah, okay, good. Wait. Oh, hold on one second. Things are happening in the chat. I do love this chat. Bear with me for a second. All needs will be met, or did he already? Okay. So yes to Alexis. Now I'm going to expand on the Alexis Morgan thing here. Oh, cool, right? But cool, okay. But bear with me, because this is another one of these things. I'm going to say some things that maybe you think you already know, but you might not have thought of in this context before. Or you didn't know that they were this important or whatever. So just bear. You never know what you don't. Okay, sidebar. Just defense of my whole life here, because I am here to try to say a lot of things that, in fact, I do think you know already, but I'm trying to rearrange the furniture in your mind. Like, seriously, I'm trying to be as clear as I can. I'm not trying to just pull things out of the air and say things that you've never heard before. Like, that's confusing. I'm trying to break down physics to things that you do already know. But then the risk of that is that often people think, like, well, I already know that, I already know that, I already know that. So then, like, they tune out or whatever. No. The whole deal is that we're trying to, all of physics is supposed to be an expansion and logical derivation of things that we all already accept. Physics, when it's done right, is a bunch of baby steps from things that we already accept. And then the baby steps all add up to surprises. And you never know when the surprises are going to come. And you never know exactly when you're all of a sudden at a place that you thought was familiar, but now it's like a new twist. So just bear with me. And what I'm trying to say is this. An angle, by definition, is a fraction of a circle, like literally a fraction, like a dimensionless fraction of a circle. You might remember from math that the definition of an angle theta measured in radians is arc length measured in meters divided by radius measured in meters. The meters cancel out, and what you have is a pure ratio, a fraction. What an angle is telling you is how much of a circle you've carved out. That's what an angle is, right? If you think about it literally, like, the whole point of an angle is it's a portion of a circle, and it's taking advantage of the fact that there's a relationship between circumference and radius in a circle that stands constant no matter how big the circle is, right? So what I'm saying is, now this is the part that you always knew, but you might not have thought of this way, okay? This right here, wait, let me just, erase my thing so I can see. When I go like this, can you, yeah, more or less, like, all of you know that's a right angle, right? You all know, and you can call it 90 degrees if you want to live in degree land, okay? Or you can go up pi over 2 radians, which is better ultimately, but whichever one you're like habituated to say, what you all know, well, I'm not doing it, you all can recognize, hello, I can't, like, the whole mirror image thing is freaking me out. Okay, you know, a right, or the things in the background of me, the buildings, the edges of the buildings, blah, blah, you all know. Okay, I'm going to look at that Sarah thing in 1 second. I'm going to respond in 1 second. But let me just say this. You all can recognize a right angle, no matter how long the lines are, right? This is the thing about an angle. An angle is about the interval between the two lines, but it's not the distance between the two lines. You can't draw a straight line from one hand to the other and say, oh, see, it's that long, that's why that's a right angle. That would just be distance. That's not angle, right? It has something. It's how far apart, it's how far one line opened from the other in a manner that is independent of the length of those two lines, right? Like, in other words, when you recognize that this is a right angle, what you're really recognizing is that this is a fourth of a circle. And just like my son, the 8-year-old, right? He knows what a 360 no scope is, so to speak, right? He knows what a 360 is. He knows it means full circle. And he knows, therefore, okay, thank you. And he knows, therefore, that a 180 is a half circle. Like, right? He's not thinking, and he's right. I mean, he's totally right, right? But think about it. It all stems from circles. What an angle is a portion of a circle. Whether you call it 45 degrees or pi over 4 or whatever, what you're talking about is dividing a circle into certain smaller and smaller portions. And the whole thing rests on the idea that it doesn't matter how big your circle is. The angle is still the angle. Right? So it's literally how much crust, and I know there's things in the chat, or there's at least one I will get to in a second, but I really want to reinforce this point, because radians I never understood, and I certainly didn't understand how cosines of radians or angular frequency had anything to do with masses going back and forth on springs until I realized that an angle is a portion of a circle. A radian is a measurement of a certain portion of a circle. So when we use radians, what we're really doing is measuring, we're using a unit of measurement that helps us measure portions of cycles. We use radians when something is going back and forth cyclically, because the radian is a measurement of a certain portion of the cycle, regardless of how long the cycle is in meters. Just like a radian is a portion of a circle, regardless of how big the radius of that circle is, right? In other words, a radian is, and I totally am remembering the chat, I promise, but a radian is like how much crust of the pizza you get per every unit of radius that you have for that pizza pie, right? Like it's taking into account the fact, like the reason that an angle is S over R is what we're saying is, well, basically we're talking about how much crust you get out of that circle. But of course, if you made the circle twice as big, if you have twice as much of a pizza, you're going to get twice as much crust for any given slice that you cut. So we're saying it's like how much crust you get per every unit of radius that you have. In the end of the, so I'm going to say this before I get to the chat. Again, I hate to keep the chat person waiting, but to get really, I mean, so if you're with me, that a radian is a portion of a circle that is independent of how large the circle is. And we're therefore going to use radians as portions of cycles that will work for us no matter if the cycle is from 0.15 meters to negative 0.15 meters or 0.3 meters to whatever. The whole idea is to be able to look at cycles independent of the size of the thing that's cycling, right? And why this all works is that all circles have a circumference that is 2 pi times their radius, right? So bear with me for a second. I just want to spit this out, and then I'll get the chat person. For all circles, the circumference of any given circle is 2 pi, that number that you all know, times the radius of that circle, right? Therefore, if you go like, therefore, around a full circle, the angle that encompasses a full circle, what my son calls a 360 no scope, just because he just got that, like he just like memorized that from Fortnite or whatever, just like we all just memorized 360 from 3rd grade geometry or whatever. And we got used to the phrase 360 so that we started believing that we understood degrees. We didn't. We just memorized that 360 was a full circle. There's no logic to, I mean, there's logic, but not that's in our heads. There's history to it. But we just accepted that a circle could be divided into 360 parts, and when you go around the full circle, we're going to call that a 360. Well, similarly, we can say if you go around a full circle and you use the definition of angle that it is arc length divided by radius, if you go around a full circle, you would go 2 pi r divided by the radius, right? The circumference, the perimeter of a full circumference is called 2 pi r. Divide that by the radius, and you get 2 pi of these units that we're going to call radians. I will get to the chat, but just now I know you've seen this before, but now I want you to see this in a new way now that might help for physics. I'm saying that what my son calls a 360 no scope, I'm going to call 2 pi radians. 2 pi radians literally just means the angle that is a full circle. That's a full circle, 2 pi radians, right? Therefore, a half circle is of course pi radians, right? And a quarter circle is of course pi over 2 radians. So radians are just my word for, dividing a circle into portions, but instead of dividing it into 360 portions, I'm dividing it into what I consider to be more direct. And if you say in the end of the day, okay, fine, but then what is a radian? I say to you, well, if 2 pi radians, well, so et cetera, right, et cetera, all the way down the line, like an eighth of a circle is pi over 4 radians, et cetera. But therefore, if you say, well, what's a radian then? Well, I say, well, look, 2 pi radians is a full circle. So that means approximately, if you want perspective on this, that means approximately 6 radians is approximately a full circle, just to get perspective. Like a little bit more than 6 radians is a full circle. Why? Because pi is 3.14, right? So 2 times pi is like 6.28. So 6.28 radians approximately is a full circle. Okay, rounding to 6, just for perspective here. So if you ask me, if anybody asks, so what's a radian? From here on in, what a radian is, 1 radian, okay, is approximately a 1/6 of a circle. Approximately, if you want to be more exact, you can say it's 1 over 6.28 of a circle, blah, 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 blah. But I'm just trying to give you a feel here, especially as a physicist, as a measurement. When I say radian, so to go all the way back, and then I promise I'm going to look in the chat, but to go all the way back to this business of angular frequency being measured in radians per second, angular frequency, by all this reasoning, measures the number of radians that something sweeps through or traverses or complete. Angular frequency, omega, measures the number of radians per second that this mass on this spring undergoes. How the heck is this mass on this spring undergoing radians per second? Because a radian is approximately a sixth of a cycle. When we measure omega, or when we talk about omega, radians per second, we're just talking about cycle sixths per second. Exactly? No, approximately. So you could be more exact if you want to, but first just get a feel for what I'm saying. A radian is a sixth of a cycle. If I say number of cycle sixths per second, if for example, and I know I keep saying this, but I just want to spit this all out and then I'll get to the chat. If omega equals 2 pi radians per second, that means the mass is completing one cycle per second. If omega equals 1 radian per second, like pi doesn't have to be in the number. If omega equals 1 radian per second, then the mass is completing approximately a sixth of a cycle per second. That's what it means. It's measuring cycles per second, only divided by 6. Why? Why divided by 6 or why? Because we already have the mathematics of circles and they involve necessarily pi. All the mathematics of circles can be constant from one circle to the next if we involve pi. So we're grafting that mathematics on the physics of something, of anything cyclical, and we're using pi and radians to capture anything that's cyclical. So at the end of the day, when we talk about radians per second, there's just a conversion factor. In fact, there's just a conversion factor of 2 pi. So I'm literally going to, okay, well, 1 second. Omega equals 1 radian per second. Then it's approximately 1/6 of a cycle per second. I still have more to say about this, as you can imagine, but I know I've said a lot. I'm going to look in the chat. But what I'm trying to say right now is omega measures radians per second. What a radian is, from here on in physics, a radian is a sixth, slightly less than a sixth of a cycle. To measure radians per second is to measure cycles per second. The reason angles are coming up is because angles are actually portions of cycles. There's no actual circle or curvature in this motion, but there is cycles, hence the radians. And that's, yes, how you link this to cosines, which are linked to circles, because the relationship between all three is the cyclical nature. Okay, I'm going to pause. There's things in the chat. Maybe there's only one thing in the chat. Sarah, so it's a relative point. I'm not, so okay, so Sarah's thing I think is good and helpful, and she should definitely submit it for points. To be honest, I don't 100% understand it. She might have to expand. I know it was like 20 minutes ago, but yes, an angle is a little bit abstract. An angle is a way of measuring. An angle measurement is a relational measurement. Well, I don't know. I guess I want to say yes. I'm not entirely sure what you mean by relative point of measurement in an abstract sense, but yes, an angle it's abstract in that angle doesn't have ultimately any, it's not about meters or seconds or kilograms. It's a pure fraction. An angle is a pure fraction of a cycle, which is how it comes into play with any system oscillating back and forth cyclically like this one. I don't know. Sarah might expand later. I don't know if I've answered Sarah's question or not, but okay. I'm going to, sorry. Hold on. There's something good in direct chat here. Okay. Yes. So someone's asking me, and that's great. Direct chat person, there's only one of you. So if you just wrote something in direct chat at 6:09, totally appreciate it. And you should totally submit that for points. It's a very fair question. So someone just in direct chat wrote, do I mind rewording the part in black because they're not really understanding? That's totally fair, partly because my handwriting is disastrous. But also, yes, I'll read it out loud just so you know what I'm saying. But yes, then I'm going to rephrase it and redo it on the next page. What it says is it says if omega equals 2 pi radians per second, for example, like all of what I'm trying to do right now is define for everybody what we mean by omega, what we mean by angular frequency, and like why it's coming into play. Like, because, you know, in a way, again, this whole midterm that you're going to have, in a way, it's a big exam on the nature of omega. It's really all about, like, do we understand omega angular frequency? Because that is the new concept here. Again, let me say to everybody, it was not expected that you understood omega before this class. It is understood that you got exposed to it for the first time in lab. It's not expected that that meant you immediately understood it. It means you got exposed to it in lab and you started thinking about it in lab. Now I'm trying to explain it more. Let me tell you again, this is meant to be a new concept. I am eventually expecting you to understand it by the time you take the exam, but in a big way, the exam is about understanding omega, which is angular frequency. Now, what is angular frequency? What I'm trying to say here is that angular frequency is a measurement of cycle completion. It's used anytime we have something oscillating cyclically. So, for example, this mass going back and forth on a spring. I want to be clear to everybody again, there's no angles. Like there's no left turns, there's no right turns, there's no curves. There's just something going back and forth along an x-axis while the clock ticks, like while the t-axis occurs. So why the heck are we talking about angular frequency? Because what I'm trying to drum in right now, in a way for the first time, is that an angle from here on in your life should really be thought of as a portion of a circle, which is to say a portion of a cycle. So for example, and the key point is that the key conversion factor, if you like, is that there are 2 pi radians to every circle or to every cycle. A full cycle from here on in life, the definition of a full cycle is 2 pi radians, or the definition of 2 pi radians is a full cycle. Or so therefore, what I'm saying in the black at the bottom of this page to the direct chat. Oh, okay. Oh, cool. And so, okay. So I'm going to rephrase right now what I'm saying in the black here, but I'm going to give you equations for it in a second. That'll make it more concrete for some of you. But what I'm saying right now, I'm giving an example of how omega works. I'm saying if you have an omega, because omega from now on is going to be a constant called angular frequency. So like, what does it mean? And it's going to go right directly before the t in that cosine function. So what does it mean to have an omega? Let's say someone says the omega for this mass on the spring. Let's say they say the omega is 2 pi. Well, okay, like the constant for this spring, for this mass on the spring is the constant that goes right before the t. Let's say they say is 2 pi, i.e. 2 pi radians per second. Like, what are they saying? What does that mean? I'm here to say what it means is it's the frequency at which this thing completes cycles. If someone says it's doing 2 pi, if someone's referring to a mass going back and forth on a spring, and they say it's completing 2 pi radians per second, to most of us, that sounds like so obscure that I've lost many of you already, just even bringing it up. I'm here to translate for you. I'm here to say, if someone says the angular frequency of a mass on a spring is 2 pi radians per second, what they're saying is every second the mass completes 2 pi radians. And what is 2 pi radians? It's a full cycle. So what they're saying, if they say that the omega for a mass going back and forth on a spring is 2 pi radians per second, they're saying this mass goes all the way from here, all the way to there, and all the way back every second. They're saying a full cycle is a closed path, a round trip, there and back. So 2 pi radians is there and back. If they said that the omega was pi radians per second, they'd be saying it only does a half cycle every second. It's like slower, in other words. If they said pi over 2 radians per second, they're saying it completes a quarter cycle. It only like gets to the equilibrium position and then comes back in a second. It's a rate at which the thing completes portions of a cycle. I'm going to expand that on the next page in direct equations that might help some of you, but let me just see the direct chat. Yes. Yes, direct chat person. All right, so hold on. Things are happening. Things are happening. By the way, I also have to praise this class. I'm definitely noticing if I add up all the public chats and the direct chat, just so you all know, I'm getting contributions from a lot of different, like there are people that are saying things right now in direct chat that like are not the same people that say something every, like I feel like a lot of you are saying a lot of things, which I really appreciate. So hang on one second. Oh, and then one of you in direct chat just actually said it clicked. I get it now. Thank you. That means a lot. Even if it does, it really helps a lot. And for those of you who think I'm going too slow or think I'm saying the same, which the people that then say when they get it you're helping each other by doing that. Or if you say you don't get it. So I totally appreciate it. Okay. Cool. Okay. So now, but I am going to now give you 3 equations based on this that you may or may not have gotten. So those of you, this will help it more for some of you who still don't get it. And it all takes practice. Obviously, it all takes practice. But for those of you who still don't get it, I'm going to give you 3 equations now that might make it seem more concrete. And for those of you who are bored and think I got it 20 minutes ago, maybe 3 equations will make you feel like you're getting some new knowledge. Here's what I'm saying. Well, wait. Okay. Okay. Well. Actually, let me do this on the next page. Hold on a second. Let me pause before I turn the page. Let me wait, where's you? Okay. No, I love what you guys are doing with the chat, seriously. Again, notice everything we're talking about now, the mass going back and forth in the spring, or the pendulum that you did, I think, in the second line. The whole issue here, the whole topic right now, the whole topic of the first midterm is oscillation, and what we're ultimately going to call this very special type of oscillation called harmonic oscillation. But I haven't even defined that yet. Right now, I'm just picturing in my mind that we're talking about oscillators. We're talking about things that undergo cycles, that do the same thing over and over again. Specifically, they go somewhere and they come back. They make round trips. They make closed paths. They make closed paths over and over and over again. Now, the closed paths right now are all one-dimensional, like to keep the math somewhat contained. So everything is like, I mean, even a pendulum that's going like this is like a one-dimensional arc back and forth, right? But everything we're talking about now, the commonality is that they're all cyclical type motions. And notice from question 8 in the original homework, they're simple in some ways because they're cyclical, and there's like a force that's like directly proportional to displacement. So something about them seems simple, but there's something very complicated about these motions, something that disabled us from ever really studying them in Physics 203. Because as you noticed in question 8, the thing about cycles is like at every moment in a cycle, your position is changing, your first derivative, your velocity is changing every moment, right? your acceleration is changing every moment. And your acceleration of your acceleration, like your third derivative, your jerk, is changing. Like what part of what the question 8 on homework 1 was meant to set up is, whoa, notice that these motions that seem very simple, or this motion that seems very simple, it's very hard to get a grip. There's like nothing that's obviously constant about it. Not the velocity, not the acceleration, not the jerk. There's nothing that's constant about this motion. So all of our old equations go out the window. We have to develop a new understanding for this type of motion. And the way we're developing a new understanding for this type of oscillation, this type of cyclical motion, is we're diving into the cyclical nature. Where it's saying that one thing that's constant is it does the same thing over and over and over again. So instead of focusing on meters or seconds, really, for these kinds of motions, we're going to focus on their cycles. Like we don't care whether the thing goes 30 centimeters or 50 centimeters or whatever. We just care about its cycles. So, okay, so let's define some ways of measuring cycles. Let's first of all, as you saw in lab, let's first call it capital T. This is capital T now, not lowercase, right? Lowercase t is the independent variable time. But let capital T stand for the period, the amount of time for one cycle. All these things that I'm defining right now, like assume that this would be, this is not a variable, this would be a constant for a given oscillator, as you saw in the preliminary labs, right? All kinds of things might be changing, but over time, the mass takes like a certain amount of seconds to go there and then back, and then over and over again, right? So let's call that period. Let's designate it with a capital T. Technically, it will be measured in the number of seconds per cycle, but then let's remember that a cycle is it's a word, it's a placeholder. Sometimes it's helpful, but it's not a proper unit of physics or science, right? Cycle, because a cycle could be 50 meters, or like a unit is always the same size. Like a meter is always a meter, right? A kilogram is always the same amount of mass, but a cycle could be any size. So it's not an actual, there's no such thing as us, you know what I'm saying? So cycle is just a word. It's not a technical unit of measurement. So when I say that period is measured in the number of seconds per cycle, really in the end of the day, depending on the context, we can drop the word cycle and say that period is measured in seconds now, right? Now, that's not an equation yet. That's just like a definition, a triple equal sign. That's what I mean by capital T period. But similarly then, from now on, let lowercase f stand for what we're going to call standard frequency, meaning the number of cycles completed for some cyclical motion per second. Okay, now this is also would be constant for a given oscillator, presumably, or the kind of oscillators we're studying anyway. Constant. It doesn't mean it's constant from one oscillator to the next, but for a given oscillator, constant for given oscillator. And the units of this, so the units of this F, oh God, we're almost at, okay, I have to get back to the thing. I know the units of F would be, so cycles per second, right? But that's a little awkward because cycles aren't, cycles aren't really a proper unit. So the units of F really properly, the units of F are seconds, and I am watching the clock now, and so I am going to race a little bit to get back to the point, but the units of F would be seconds to the -1, but that's severely awkward and bizarre, right? So we have a word for that. We have a derived unit called a hertz, which is defined to be 1 cycle per second. Okay, so what I'm talking about now is standard frequency, like the number of times something goes back and forth per seconds of time. So if something completes 1,000 cycles per second, we say it has a standard frequency of 1,000 hertz, or in other words, 1 kilohertz. That's what, and if it did 1,000,000 cycles per second, we would say that's a megahertz, right? Hertz is literally a cycle per second. It's a measurement of standard frequency. Now, if you're following me, and I know we have 20 minutes left, so bear with me. If you're following me, you'll notice like this is like this sounds related to what I was talking about before, but it's a little bit different. This is literally the inverse of period, right? If you're following what I'm saying, it's absolutely an equation. Therefore, like standard frequency is the reciprocal of period, or vice versa. Sorry, you could say period is the reciprocal, the multiplicative inverse of standard frequency, right? Meaning, if it takes me 4 seconds to complete a cycle, if it takes me 4 seconds to go there and back, if it takes me 4 seconds to go there and back, that means I'm doing 1/4 of a cycle every second, right? Standard frequency just measures, so period measures the thing that's easiest to observe in the lab and easiest to picture in our mind. Period is how much time it takes to do a cycle. Standard frequency is the next step from that, is the inverse of that. If period is how much time it takes you to do a cycle, then standard frequency is how many cycles you do per time. And then one step removed from that, the most abstract of all, but the most mathematically useful, is angular frequency, to bring this all full circle, right? What angular frequency is, the radians per second, is 2 pi times the standard frequency. Or in other words, omega is 2 pi over period. What I'm saying now, let this sink in. You can memorize it for the moment if you want, if it helps make things, but I'm trying to put together 3 concepts. I'm saying, and maybe try to write, I'm going to say this, try to write it down in your own words and screenshot and submit, for points if you want. I'm saying there's 3 distinct ways we could measure the rate of cycling for some kind of oscillator. There's 3 different ways we could measure how much time the oscillator takes to complete a cycle. That's called period. We can measure how many cycles it completes per second. We can measure that in hertz, and that's called standard frequency. Or we can measure the angular frequency, how much radians it covers per second, and that would just be the standard frequency times 2 pi radians. In other words, sorry, that's not what I meant to do. Oh, yes, I will. Yes, good question. Hold on, I totally will. Hold on 1 second. So yeah, someone's asking me to repeat. Wait, I'm gonna repeat. Yeah. Okay. So I'm gonna repeat. There's 3 different ways we can measure how rapidly an oscillator cycles. We can measure how much time the oscillator takes to do a complete cycle. That would be called period. That's measured in seconds, right? And that's the most direct, easy thing to measure, and really the most direct, easy thing for any of us to picture in our minds, how many seconds there are per cycle. Or method number 2, we could measure, or we could picture in our minds the inverse of that. We could picture how many cycles something completes per second, right? Not how many seconds it takes to complete a cycle, but how many cycles the thing completes per second. And that would be called standard frequency. That would be measured in not seconds per cycle, but cycles per second, which are called hertz. So first, you can measure the period of something in seconds, or you could measure the frequency of an oscillator in, you can measure the period of an oscillator in seconds per cycle, or you could measure the standard frequency of an oscillator in hertz, which are cycles per second, or you could measure the angular, this is method 3, or yes, hold on one second. Yeah, exactly. Yes, direct chat person. Totally, yes. Those are the 3 equations. Yes. And the third method is that you could measure the angular frequency of something in radians per second, not in hertz, not how many cycles it did per second, but how many radians it did per second. And all you got to do to get to that third one is use this conversion factor of 2 pi radians per every cycle, right? So if something had a standard frequency, let me back up. So wait, so those are the 3 different methods. I'm going to give you an example again in a moment, but you've got 3 different ways of measuring how rapidly something cycles. You've got period, standard frequency, and angular frequency. You've got period measured in seconds per cycle. You've got standard frequency measured in hertz, which is really cycles per second. And you've got angular frequency measured in radians per second. Any one of those 3 will get you the other 2. They're all linked by these 3 equations, however you want to write them. If you know one, you automatically know the other 2. You can convert back and forth by flipping one or multiplying by 2 pi. Basically, the key thing to know is that there are 2 pi radians for every cycle. If you're following me so far, there's at least one of you in the room who's thinking, actually, I do get this now. There's one of you at least thinking something like this. I do get this now. Okay, 3 distinct ways to measure the same thing. Okay, angular frequency is just like ultimately like 2 pi multiplied by the regular frequency. The regular frequency was the thing I always understood. Okay, I get this now. But then you're thinking, at least one person thinking, I guess I get this now. But then if all those 3 things measure the same thing, if you know one, you automatically get the other 2. Why the hell do we have to worry about excuse my language. But one person's thinking, I get it just enough to not understand why we need this freaking omega thing. Why doesn't it just stick, Yaverbaum stick to period and standard frequency? If you're thinking that at all, you're totally with me. And here's why. Period is the easiest for all of us to understand and to measure in the lab. But angular frequency is the easiest to use in the math and the physics, i.e. in the cosine function that prompted all of this in the first place, and which I need to get back to answer the last question of homework 1. The function that's going to answer all of our problems is a cosine function, and cosine grafts our knowledge of circles onto our situation of cycles. So we need radians to do the math. Nobody likes radians any more than you do. It's not like we want to be using radians. They're not intuitive to any of us, including you, but they're the mathematically useful ones. So period. Okay, well, fine. And actually, so do I at this point. But I'm saying if you don't like them yet, fair enough. I like Evelyn, by the way, period. But if you don't like them yet, hang in there. Or if you're just thinking that I'm just making them up to make you miserable, no. What we're saying is period is what we see in the lab. Angular frequency radians is what the math accepts. And standard frequency hertz is the bridge between the 2. Whatever one we use, we can go to the other 2. So it's depending on whether we're doing the math theory analysis or we're doing the lab experimentation, whether we're talking period or angular frequency, but standard frequency is the bridge between the 2. That's why we have all 3. Let me now go back to these radians and to this cosine thing so I can at least wrap this up before 6:45. But I think but yes, these are the 3 equations that relate to all. Bottom line, if someone says there's a standard frequency of 2 cycles per second, if they're like, that thing is doing 2 cycles per second. Well, I'll even start. I'm going to do this example fast. You can write it down if you can. And if you can't, don't worry about it. You'll see it a million times again. But if someone walks in and says, oh, I'm in the lab, and that thing takes, if they say that thing takes 4 seconds to do a complete cycle, right? Because they measured it, because that's the easiest thing to measure. Then I could say, oh, it takes 4 seconds to do a complete cycle. I guess that means it's doing 1/4 cycles per second, right? Its standard frequency, therefore, is 1/4 hertz. And then I can say to myself, to plug into the math that we're about to do, I could say, oh, if it's doing 1/4 cycles per second, if it's doing a standard frequency of 1/4 hertz, then what I guess that means is it's doing pi over 2 radians per second. Its angular frequency, omega, must be pi over 2 radians per second if it's got a standard frequency of 1/4 hertz. If you follow that, and you can write it down, you should totally post it for points because it'll totally show me that you're with me. If something has a period of 4 seconds, then it has a standard frequency of 1/4 hertz, and therefore it has an angular frequency of pi over 2 radians per second. And therefore we can plug that into the cosine function. If you follow that, you're good, you're with me, and maybe you're even bored. So I'm going to move on. But that's what I'm saying so far. I'm going to move back to the cosine function. This is what we have so far. We're guessing, right? We have 10 minutes. Okay. We're guessing that we have x equals something times cosine of omega t, where omega is this whole big discussion that we just had. Okay. This is still a guess. Now, why am I leaving a blank before the cosine? I could be faster now with this part. Same reason, units. Okay. You take the cosine of anything, of radians, it's going to spit out a number anywhere between -1 and 1. But and -1 and 1, nothing's unitless, right? This equation is supposed to be spitting out some number of meters that's not necessarily between 1 and -1, but between whatever the original amplitude was and the negative amplitude, right? So to cut to the chase, we need something before the cosine that will scale up the whole thing, that will multiply that whole cosine graph and make it so that it doesn't just start at 1, but starts at wherever in meters the mass actually started. In other words, what should go here is x naught measured in meters, right? And if you think about, I'm going fast now, but you did the hard part already. If you followed all the part before, you can follow this. I'm guessing, I haven't proven yet, but I think I have very good grounds to guess that my function has to have an x naught before the cosine, some kind of value of x, the value of x when t equals 0. When t equals 0, the cosine of anything times 0 will be 1. So x naught's got to be some number of meters that's multiplied by 1, like the maximum number of meters that this thing will reach or was at when t equals 0, right? I'm saying that fast, but I think you're with me. And sometimes, as you see in homework 2, like x naught means the initial value of x, but as we find out, because of energy conservation, that initial value is the most that the displacement's ever going to be. So another word for that, so that's the initial displacement, right, from equilibrium. But due to energy conservation, x max must, well, x naught must be x max. And we have a word for that. It's called amplitude, the maximum displacement from equilibrium. So often we use the letter A interchangeably with the letter x naught. I'm going to move on. I'm just saying again for clarification, A and x naught, they technically mean different things. X naught technically means the first value. A technically means the maximum value, but they are one and the same for an oscillator like this. So in homework 1 and homework 2, it goes back and forth and uses both. Okay. But now with 7 minutes left, this is now our guess. This is our best guess. We are guessing. We're conjecturing that the position time function for an oscillator of this kind, we're conjecturing that it looks something like that, right? Or you could write it as x equals a cosine omega t, right? Now, that doesn't mean it's right. My whole explanation now was to try to get you to see why this didn't come out of nowhere, where the sense behind this guess, but it's still just an educated guess. I didn't prove. Oh, sorry. Now, and sorry. No, really good. I'm going to answer this quick, and then I'm going to ask, I know usually I love the chat and everything, but since I have at least 6 minutes and I want to get us to closure, I'm going to answer this question and I'm going to ask us to hold our questions for a couple of minutes. But yes, Alexis's question is a great one. Sine omega t would also work, except for one thing. Remember that sine of 0 equals 0. So if we don't adjust the sign in any way, it will work like this, but it won't be quite as convenient if it's just left alone, because it would spit out that at t equals 0, x equals 0. And we don't want that. Like our oscillators start, if x is 0 at t equals 0, the oscillator is never going to move at all, right? So we actually slightly prefer the cosine function for this context. But yes, you could certainly add a term to the sine function to make it work like the, and we'll get to that eventually. But so I guess my strict answer to Alexis, besides saying great question, is they're almost equivalent if you make a proper adjustment, but they're not strictly equivalent, for whatever that's worth. Okay. You're right. There you go. Okay. What Evelyn said. Yeah. What she said. Okay. So now here's my conjecture. We've got 5 minutes left. I haven't this was all me being a scientist, in effect, building up my theory. Now I have to be a mathematician and actually verify my theory. Remember the original issue. We want. Cool, right. I agree with everybody. Yes, good Evelyn and good everybody who liked Evelyn or whatever. Yes. But remember, but now let's just everybody bear with me for these 5 minutes, or stay with me for 5 minutes. And then again, when we're done, I will hang out and answer any questions slowly to anybody or whatever. But let me get this done so you can go home. And just keep working on, if this helps you go back and correct. Well, what I'm about to do, not only will complete homework 1 for real, for those who've been waiting this long, but also it completes the first 2 exercises at least of homework 2. So we'll get to a fly. So you still have another night to complete that if you want, and we'll get off to a flying start with it tomorrow. Here we go. We remember we want an x as a function of t such that, like the whole issue was, we want an x such that when you differentiate it twice, you get negative times some constant times x itself. Well, how can we test? The way to test this now, we couldn't get at this by taking antiderivatives or derivatives. We could not, as 2 people said, but now that we have a guess, we can test it directly. We can prove it's right or wrong by taking derivatives. Let's take our function that I'm testing. The function that I'm testing is right here. This is what I'm testing. So I'm going to take the first derivative of that. And I'm going to do it fast. I'll do this a little bit more slowly tomorrow for the sake of homework 2. But I'm going to take the first derivative of this. Now I'm going to use chain rule, and I'm going to use, because I have 3 minutes, I'm just going to do it. I'm going to use chain rule, and I'm going to use trigonometric derivatives. I'm going to say that the derivative is negative x naught omega times sine of omega t. Either you, right? Because I used chain, I did a function of a function. The inner function is omega t. So I had to multiply my whole answer by omega. And what was my answer? My answer was the derivative of cosine is negative sine. I will do that more slowly tomorrow. So make a note of it. If you don't like that, you can ask about it tomorrow. But just to complete this, I'm going to keep going right now. That's the first derivative of x naught cosine omega t. It's negative x naught omega sine omega t. Now I'm going to take a second derivative. Why? Because I'm trying to test out whether the second derivative does indeed return the thing it's supposed to or not. So I'm going to take the derivative again. I get negative x naught omega times another omega. In other words, omega comes out again from chain rule. So I get negative x naught omega squared. But now the derivative of negative sine is not cosine. It's negative cosine, if you know what I'm saying. I'll say that again slowly tomorrow. But this is the derivative of that. So now look, and we have 2 minutes. Just look with me for a second. Apparent, like what is this? What does that prove? What is this nonsense? Well, I'm just going to rearrange slightly. Multiplication is commutative. I'm going to say I get negative omega squared x naught cosine omega t. I just rearranged the first 2 constants. They're just constants. So I just shifted the order of multiplication, right? So what does that do for me? Well, notice everything in the parentheses here, this whole business in the parentheses, that is what I conjectured x to be, right? So evidently, when I differentiated this thing twice, with 1 minute left of class. When I differentiated it twice, what I got was negative times some constant times x itself. That's what I was supposed to get. Negative times some constant times x itself. The constant over here in the original math was written as k over m. The constant over here is written as omega squared. They're both constants. In other words, this solution works. This solution, x equals x, and this is my last thing I'm saying, and then this solution works as long as omega squared is just another name for k over m. So actually, the last thing I'm saying, we just got two pieces of information for the price of one. We just learned that x equals x naught cosine omega t solution is the solution. It is the equation we're looking for to plug in. We can literally now plug in 1 for t and 200 for k, blah, 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 plug into that, and it'll spit out an x for us. What do we plug in for omega? We apparently plug in the square root of k over m. What we just learned here is our solution works as long as the rate at which this thing goes back and forth is the square root of its stiffness divided by its mass. We actually learned two things at once. We learned what the solution to this differential equation is, and we learned how the constant rate of oscillation depends on the parameters of the system. So you plug in. So you literally plug in x equals 0.15 times cosine of square root of 200 over 0.3 all times 1. And you plug in with your calculator in radian mode, because everything we just said was about radians. And if you plug in, you will get that x approximately equals 0.116 meters. So that's homework 1. And if you look, you'll see it's also really the first 2 questions of homework 2. That's it for you've been very, very patient. You've also been very, very smart. Wait, really? Awesome. Oh my God. Oh, cool. I'm so glad. Okay. No, I'm glad. Awesome. I'm glad if this made any sense. And we will go a little slower when we start tomorrow. I promise. And you can definitely ask questions. But great. And you can hang out. But so thank you. You can go home. You've been very good. But I'm here if there's questions now, and I'll turn off the recording. Thank you guys. Okay. Thank you. Yes. Have a great, thank you. Have a great.
Thank you. Have a nice day.
Thank you guys.
I have
Really.
a question.
Okay, let me turn off the recording. I mean, unless you want to be, hold on one second. But yes, have a good one. Yeah, hang out for 1 second. Thank you guys. Thank you guys. Okay, I'm stopping the recording. I'm trying to hold on one second. Okay, okay.